Okay. Thank you. All right, so we've been talking about neutralization and titration problems. Last week we looked at a strong acid with a strong base. And we looked at a weak acid with a strong base. Now, other possibilities, we could have a strong acid with a weak base, and we could have a weak acid with a weak base. Now, we aren't going to spend any time looking at this last combination. Those calculations tend to be significantly more complex than the types of calculations that I would rather have you guys focus on. So that leaves us with three categories. And we've covered these too. And I thought a lot about this over the weekend. And I debated with myself whether or not I wanted to actually tackle the third category, or if I just wanted you guys to focus on the first two. And I decided that I want you guys to focus on the first two. You guys need to, because I'm cutting out a third of the material, make sure that you spend significant time studying these two types of problems. The strong acid and weak base calculations aren't any tougher than a weak acid with a strong base. But conceptualizing and thinking about what's going on in that solution when you add a weak acid with a strong acid with a weak base is a little bit tougher. Because imagining what's going on in the solution, the concept of what's going on in the solution is harder, these tend to be more of a struggle for students. So I'm going to cut out the two hardest combinations in hopes that you guys will then be able to focus your attention on these two categories and do really, really well in those two categories. So my expectations are quite high considering I'm removing this third piece. Does that make sense? Okay, so we're done with neutralization and titration then. That brings us then to the next portion, which is on buffer solutions and salts. Well, if we're going to be talking about buffer solutions, we should probably define it so we understand what a buffer solution is. All right, a solution that contains a weak acid and its conjugate base, or a weak base and its conjugate acid. Buffer solutions resist pH changes when an acid or a base is added to them. There's two common ways that buffer solutions can be made. The first would be taking a weak acid and a salt that has the conjugate base as part of it and mixing those together in solution. Or a weak base and a salt that has the conjugate acid and mixing those together in solution. Or partially neutralizing a weak acid with a strong base will create a buffer solution. Or partially neutralizing a weak base with a strong acid will create a buffer solution. So we can either dissolve an acid and a salt that contains its conjugate, or a base and a salt that contains its conjugate in solution to create a buffer solution, or we can do a partial neutralization to create a buffer solution. Let's take a look at a problem where we have an acid and a salt dissolved in solution. Thus, we have a buffer solution. And let's look at calculating its pH. And we have a solution that has acetic acid and sodium acetate dissolved in it. There's enough acetic acid dissolved to make a 0.5 molar solution and enough sodium acetate dissolved to make a 0.5 molar solution. We have a weak acid. And because our salt has the acetate ion, we have its conjugate. So this is a buffer solution. And we can actually calculate the pH of this quite easily using the Henderson-Hasselbalch equation that we talked about last week. pH is equal to the pKa plus the log of the concentration of the negative ion over the concentration of the acid. Oh, and I should mention that the Ka for acetic acid is 1.8 times 10 to the minus 5th. That will also be important information for us. Okay, so really we just need to figure out how much acid we have in solution and how much negative ion we have in solution. Well, how much acid do we have in solution? We know we have a 0.50 molar solution, so that's what we'll plug in there. How much of the acetate ion do we have in solution? We have a 0.50 molar sodium acetate solution. Sodium acetate is Na(C2H3O2). For every one sodium acetate that breaks apart in solution, we'll get one acetate ion. Because it's a 1-to-1 ratio, the concentration of the acetate ion would also be 0.50 molar, so we can plug that in there. And we can calculate. Now, I know some of you are probably thinking, well, what about some of those side reactions that might be going on? Wouldn't the acetate ion be reacting with water since it's a stronger conjugate base? Wouldn't that be forming some acid and taking away from some of the sodium acetate? And wouldn't the acid be ionizing in solution, making some of the acetate ion as well? But the amounts that those things are happening, the amounts that are created by those things happening, or the amounts that are used by those things happening, are not significant compared to the large amount that we have just present in the solution from dissolving this much acid and this much sodium acetate. So those changes will not significantly affect these amounts. So we can just plug those in. So pH will be equal to the negative log of 1.8 times 10 to the minus fifth plus the log of 0.50 molar divided by 0.50 molar. 0.50 over 0.50 is 1. The log of 1 is 0. So to calculate this, we just need to take the negative log of 1.8 times 10 to the minus fifth. Now, that doesn't always happen like that, but the best buffer solutions have a pH that's equal to the pKa. So the negative ion concentration and the acid concentration are equal or almost equal. So the best buffers have a pH that's equal to the pKa or close to it. So we're going to see very similar concentrations of negative ion and of acid in solutions that are good buffer solutions, that are good resistors of pH change. What is the pH? 4.74, and great with sig figs. We need 2 decimal places because we have 2 significant figures here, 2 significant figures here. So that corresponds to 2 decimal places in the pH. All right, now we said that a buffer solution is a solution that contains a weak acid and its conjugate, or weak base and its conjugate. And we can calculate the pH of the solution as we just did. I also mentioned that a characteristic of a buffer solution was that it was a good resistor of pH change. And so let's see how good it is at resisting pH change. So based on the problem above, we're going to continue and we're going to answer a second question. If 0.010 moles of sodium hydroxide is added to 1.0 liters of the above solution, what is the pH change? Once we answer that question, we're going to look at adding the same amount of sodium hydroxide to just water, so something that's not a buffer solution. And we're going to look at what the pH change is for that, and that's going to allow us to kind of verify this idea that buffer solutions are good at resisting pH change. So what would the pH change be if 0.010 moles of sodium hydroxide is added to 1.0 liters of water? So we have 1 liter of the buffer solution, 1 liter of water. And to both of them, we're going to add 0.01 moles of sodium hydroxide, and we're going to see if we can calculate how the pH changes for the buffer solution and how the pH changes for the water. We should see a very small pH change for the buffer solution. We should see a larger pH change for just adding that much sodium hydroxide to water. Let's first start with this first question. If we add sodium hydroxide to the above buffer solution, some of the sodium hydroxide, or actually all of the sodium hydroxide, will react with some of the acid. So some of the acid that's present in that buffer solution is going to get used up. So we're going to see a decrease in the amount of acid. So this number should decrease slightly. When the acid and the base react, they're going to form salt. So we're essentially forming an additional negative ion. So this is going to increase a little bit. If we can figure out how much this acid concentration decreases and this negative ion concentration increases, we can plug in those values and calculate the pH, and then compare it and see how the pH changed. So let's first start by looking at how many moles of acid I have in the buffer solution above. Moles of CH3COOH. We have 1.0 liters of solution, according to our problem. And the acid is 0.50 molar. So I have 0.50 molar, 0.50 moles. Of acetic acid in the buffer solution. Okay, I have 0.010 moles of sodium hydroxide, according to the problem. If we write a reaction for sodium hydroxide reacting with acetic acid, we'll see that these react in a 1-to-1 ratio. If they react in a 1-to-1 ratio, how much of the acid will react with the sodium hydroxide? If we add 0.01 moles of sodium hydroxide, they react in a 1-to-1 ratio, how much acid will react? 0.01 moles of acid will react. So if we have 0.50 moles of acid and 0.010 moles react, we'll be left with 0.49 moles of acid that did not react that are remaining in solution. Well, perfect. I just calculated this piece here. This is going to decrease to 0.49 moles. Okay, now I have to look at how much negative ion I had, and then once this reaction between the sodium hydroxide and the acetic acid, how much negative ion will form to find out how much negative ion I now have in solution. So moles of CH3COO minus that we initially have. Well, we have a 1 liter solution, and it's 0.50 molar, 0.50 moles of acetate ion. And this is before we add the base. Once we add the base, some more acetate ion will be produced. Let's think about how much. We just said that 0.010 moles of acetic acid will react, and that's where the acetate ion comes from. And isn't this a 1-to-1 ratio? So if 0.01 moles of the acetic acid reacts, how many moles of acetate ion will form? 0.01 moles will form from this reaction. So I'll have 0.50 moles of the acetate ion plus 0.01 moles of it that form from this reaction, giving me 0.51 moles of the acetate ion after I add the base. So now I have this piece here. So to calculate then the pH, I'm going to use the negative log of Ka, 1.8 times 10 to the minus fifth, plus the log of 0.51 moles over 0.50 0.49 moles. We'll see how that changed the pH. What is that? .76 is the new pH. So what was the pH of just the buffer solution not having added any base to it? 4.74. If the pH is now 4.76, what is the pH change? 0.02. Okay, well that's not a very significant pH change. Let's look at what if we added that much base to just a liter of water, which is not obviously a buffer solution. Let's see how the pH would change in that scenario. So if we have 1.0 liters of water, and into that we're going to add 0.01 moles of sodium hydroxide. What we're essentially doing is just creating a sodium hydroxide solution, right? We have water, we dissolve sodium hydroxide into it. We could calculate the molarity then of the sodium hydroxide. 0.010 moles of sodium hydroxide is being dissolved in 1 liter. So the molarity of sodium hydroxide is 0.010 molar. Now, if we know the molarity of sodium hydroxide, because that's a strong base, what do we also know? This is also the hydroxide ion concentration in the solution. So the hydroxide ion concentration is 0.010 molar, and we can use this then to figure out what the pH would be. We can calculate pOH by taking the negative log of 0.010 molar, which is 2.00. So what will the pH be? pH is 12.00. Now, how did the pH change? If I have a liter of water, just a liter of water, what is the pH of water? 7. If it jumps up to 12, what was the change? pH change would be 5.00. Well, that's a huge change compared to a pH change of 0.02. So you guys can see that buffer solutions have the ability to resist pH changes. Why is that important? Well, your body, for example, contains buffers that resist pH changes. Our bodies don't like to fluctuate in temperature, in pH, and anything very much. And so our body contains buffer solutions which control the pH of different parts of our body. For example, if we eat something acidic, well, can you imagine if we had water in our stomachs, how much the pH could change? Okay, so we need something to control those pH changes, so our bodies use buffer solutions. Again, those of you who are taking biochem next year, you guys will get to explore the buffer systems in the body and how this stuff applies to that. Questions, comments, concerns? Okay, tomorrow we're going to move on to talking about salts. I would like you guys to take the next 15 minutes and try to do some of your practice tests. I'm going to try to give you time throughout the week to work on your practice tests. Since we're not doing that last part of neutralization titrations, I have very high expectations for how you guys are going to use your time. I do not want to feel disappointed that I cut out part of the curriculum and then you guys decided not to use your time the way that it's intended for it to be used. The weather is gorgeous. Please do your work in school where you have me to ask questions, you have your classmates, and then go enjoy yourselves after school.